All right, good evening, students. Today is Sunday, September 22nd, and this is Mr. Rich's Q&A for his tutoring students. And we've got a few students here present. And what I wanted to cover tonight is I'm going to show you a few TI-84 tips and tricks that might help you. I've got calculus students that are actually live here, so I'm probably going to scale this down a little bit and just show them a few things that might be of interest to them. If you're in AP Pre-Calc, this might be of interest to you as well as I show you a few things on the TI-84. In fact, I'm going to just show maybe one or two things here so we could get to your questions. So those of you that are here, I believe are the calculus students. If you've got questions, please post them and we can cover whatever it is that you want me to cover. I'm going to share my screen and I'm going to pull up my TI-84. I'm going to show you a few things here. This is my TI-84. One of the things that I did want to show you that you may not know about, I want to show you the key, and that there is a mode that you can put your calculator in, and you can put your calculator into complex number mode right here. So you can be in full real mode, or you can be in the mode right here. And once I'm in there, when I go back to my home screen, I can do any kind of complex number math with the I button that's right down here on the decimal. So even if you wanted to do a power of I, like, I don't know, sometimes on the ACT, they'll ask you to raise I to some ridiculous power. Well, if you take I and raise it to the 23rd power, it's going to tell you the answer is negative I. So anyways, or you could multiply complex numbers, right? You could say, I want to multiply the complex number 6 plus 3i times negative 2i. And it gives it to you as a complex number, 6 minus 12i. So that is one thing that a lot of students don't know about. Another one too that I don't see a lot of teachers telling students about is, you can store values within the letters of this calculator, your A, B, C, D, E, F, G, right? So if I get a result from a calculation, I don't know, 9 divided by 52, and I want to save it, I can tell the calculator to store that answer in location A. All right, so it's now in there. So I can always call up 6A in another calculation, right? 6A, and there it is. So there's 6 times A. And so every time you store, it's going to overwrite one of the values, one of the locations within the memory. So that is something that is, I think, quite useful that a lot of students don't know about. And I will show one other one. I think I showed this on a prior session, and it has to do with matrices. If you're a student that's taking the ACT, you will know that occasionally you run into matrix problems. And a lot of times they're not problems you could do on a calculator, but sometimes they are, right? But they'll be completely numeric. If you wanted to do some sort of matrix operation, you could enter a matrix onto your home screen. Like, suppose I needed to take 6 times some matrix. Well, there is a button here, alpha F3. If you hit alpha F3, you can create a matrix on your home screen. You give it the dimensions, the rows and the columns, and we can do, say, create. I'm going to arrow up here and say, I want it to be a 3 by 2 matrix. And then I can put in the values of the matrix. And I see a question, Alexandria says, use the chain rule with trig functions and implicit differentiation. Definitely we can do some of that. Okay. And then this, if we put in some values into our matrix, and of course it's going to matrix, multiplying a matrix by a constant, or what we call a scalar, is just distributed to all of the elements inside. So there's your matrix answer. So you can do a lot with matrices on the home screen. When you go to college, if you do take a linear algebra class, which is a class on matrices and all the applications of matrices, you have an entire menu here on your TI-84 on matrix, where you can enter matrices into your calculator And then these are all the different operations that you might want to do with a matrix. There's a lot here, incredibly powerful, but that would be something that you probably are never going to use in your life unless you do take some sort of matrix class, usually called linear algebra. It's might be a 2000 or 3000 level college class. And you know what? I think that's all I'm going to cover on the TI-84. Well, what I think I will do is do a little bit of calculus to start with. And again, I have a few other students who joined in. If you've got questions that you want me to address, put them into the Zoom chat or send me an email at askmrrich@gmail.com and I can cover that. Well, let's do a little bit of derivatives, and I'll pull up a few questions. Some of you that are a little bit more maybe advanced in the calculus journey into Unit 2 are dealing with the chain rule. Not a bad idea to take a look at that and maybe do it along with some trig functions. So let's try that. I'm going to pull up what it is that I need, and then I'll flip right back. All right, so we're going to grab this. Bear with me, I'm almost there. And the chain rule, there it is. That's what we need. That's it. I'm not going to give a formal definition of the chain rule. I'm just going to show you how the chain rule works. I'm going to explain it. There's more to it than this, but this is really what you need to know about the chain rule. I'll show you by example, basically, how to do this. Let me check one thing, though, before I do that. Let's take a look at this, this function right here. If we want to take the derivative of this function, without the chain rule, the only way that I really could do it is I'd have to expand that with like the binomial theorem. Those of you that are in pre-calc watching this probably have been taking a look at how to expand binomials in Unit 1. That's part of, I think, lesson 111. But we don't want to do that. We want to be able to get right to the derivative. So here's what the chain rule is, if you haven't seen it before. What it is I have an inside part to the function 3x minus 2, and the whole thing is being raised to the fourth power. So when we take the chain rule, what we do is we say, well, I have something 3x minus 2 raised to the fourth power. So I'm going to use the power rule. The power rule says I will take 4 times that thing, but then reduce the exponent by 1. 3x minus 2 is what that thing was. That is the power rule. But since the thing inside the parentheses was not just a regular x, it was another function, 3x minus 2, I need to multiply by the derivative of that inside part, which hopefully you know that that derivative is 3, right? If it was, just to make my point here, if you had asked me to take x to the fourth and find its derivative, no sweat, I would use the power rule. It would be 4x to the third. Now, you say, why don't you use the chain rule there? Well, in a sense, I am, because the inside part is x. So 4x to the third, but the derivative of x is 1. The derivative of this part is 1. So I don't really think of it as a chain rule. But when the thing is no longer an x, but a 3x minus 2, I need to multiply by the derivative of the inside part. That makes this derivative 12 times 3x minus 2 to the third power. That is the basic chain rule. Now, the chain rule is going to be used in conjunction with other rules like the product rule and the quotient rule. And I'll show you how that works. And then we'll get to some trig functions as well. Well, let's take a look at this one. Suppose I need to take the derivative of this. I'm going to rewrite that radical like so. I'm going to do 1/2 x squared 4 minus x squared to the 1/2 power. So I'll change the radical to a rational exponent. But this requires me to realize, hey, I got the product of 2 separate functions that I'm taking the derivative of. So therefore, it is a product rule. That's my first part of the product. That's my second product. And I'm going to use the product rule, which I'll write it like this. If you take the derivative of the product of 2 functions that I'll call f and g, I take the derivative of the first times the second plus the first times the derivative of the second. Sorry, the first f times the derivative of the second. That's the product rule. So I'm going to employ the product rule, but at the moment that I take the derivative of this second product, it then becomes chain rule, right? So here's how it works. So y prime, the derivative is derivative of the first. Well, the derivative of 1/2 x squared is 1 x to the first power times the second. So I'm just going to put 4 minus x squared to the 1/2 power. Then there is a plus in the product rule. So now I'm ready to move to the second part where I'm going to take the first function f times the derivative of the second. So this gives me 1/2 x squared. Now I'm ready to take the derivative of the 4 minus x squared to the 1/2. So that means by the power rule, the 1/2 comes to the front. I leave the inside part alone and reduce the exponent by 1, giving me a negative 1/2. And then by the chain rule, I need to multiply by the derivative of the inside part, which would make it negative 2x. Now, throwing that all together, simplifying a little bit, not much to simplify here. Over here, I have a 1/2 times a 1/2, which is 1/4 times negative 2, makes this negative 2, or negative 1/2, right? That's 1/4 times negative 2. So that's a negative 1/2 x to the third times 4 minus x squared to the negative 1/2. All right, and so that becomes the derivative. There's more to do here in terms of simplification. If I do need to, for instance, find the critical values and set the derivative equal to 0, I'm not going to do that right here. But anyways, that is a combination of product rule combined with the chain rule. All right, any questions on that? That kind of feels like we did that one before. Let me make sure I've got the chat pulled up here. There we go. All right, let's go down here. Chain rule with some trig functions. Yeah, that's a good one. We will do that one, and yeah, let's try this one here. This would be a chain rule, right? I'm taking the sine of e to the 2x. So my inner function is the e to the 2x. It's the sine of that thing. When I take the derivative then, the derivative of sine of something would be the cosine of that something. So it's cosine of e to the 2x. But then by the chain rule, I need to multiply by the derivative of e to the 2x. Well, if you know what the derivative of e to the 2x is, that is e to the 2x times the derivative of 2x, which is 2. And so then our final derivative here becomes y prime equals 2 e to the 2x times cosine of e to the 2x. And that is a chain rule problem. Now, one of the, I guess the first applications of the chain rule is in what we call implicit differentiation. And again, if you have any questions about these problems, or if you see me make a mistake, please put it in chat. If you think, or you're wondering why I did something or how I did something. I'm going to show you implicit differentiation here in just a sec, but let me do this one here. Your teacher has probably warned you about trig functions that are to the second power, sine squared of pi theta. Your teacher very well may have said, and I hope they have shown you this, that it's better to write this even before you start your chain rule like this, right? So sine squared of pi theta does mean sine of pi theta, the entire thing squared. So that means this is actually ends up being a double chain rule problem because I have sine pi theta raised to the second power. So when I take this derivative, I'm going to start with the power rule. 2 times 4 is 8. I will leave the inside part alone, sine of pi theta. I will reduce the exponent by 1 to make that a 1 power. I will not leave it there, but that is to the 1 power. But now I need to take this derivative times the derivative of the inside part that was inside those parentheses that was raised to the second power. Well, the derivative of sine of pi theta would be cosine of pi theta. But that's a chain rule, right? Because it's not just the derivative of sine of theta, it's sine pi theta. So its derivative using the chain rule is cosine pi theta, but then times the derivative of pi theta, which would be just pi. That ends up being my derivative. So it's 8 times pi, bringing that pi to the front, times sine pi theta times cosine of pi theta. That is the derivative with the chain rule. It's actually a double chain rule, right? I had something to the second power. That was my first application of the chain rule. Then when I ended up taking the derivative of the inside part, it was another chain rule. There you go. Alexandria, why is the derivative of the e just what it was times the 2? Okay, I'm going to go back because I think I know exactly what she's asking. Where did I do that? That's going to be the challenge for me to find where I was. But what I was taking the derivative of was e to the 2x. Yeah, it wasn't there. Where was that? Well, nuts. Was it up here? I bet you it was up here. Oh, oh, yeah, this one right here. Good. Thank you for asking that. Yeah, well, one of the things about the derivative of e to the 2x. So let's just as a separate rule here, one of the things that you learn early on about taking the derivatives of functions is that the derivative of e to the x is itself. It's the only function in the universe that I know of that is its own derivative. So the derivative of e to the x is e to the x. However, if you take the derivative of e to a power that is itself a function of x, it could be, in this case, it was 2x. It could have been x squared. Well, this is a chain rule problem because the derivative of e to the x squared is itself e to the x squared, but then I need to multiply it by its derivative by the chain rule. And so that derivative becomes 2x times e to the x squared. So when I was taking the derivative up here of this inside part, the derivative of e to the 2x is this right here. I hope that answers your question. If not, let me know. Awesome, awesome. Now I'm going to do implicit differentiation, and then I'm going to do a little bit of pre-calc. I'm going to go grab an implicit oh, somebody posted a question. I like it. I'm going to pull up this question and see what it looks like. I've never had somebody post a picture of a question in the chat. I didn't know it could be done. I'm glad that I know it can. I think it can, unless it just locked my system up. Uh-oh, let's see. I think it's trying to download it. I'm not sure that's going to work. It's trying. It got it. Oh my gosh. There it is. All right, I'm going to do it. I'm going to take this. Let's see if I can make it work. I'm going to pull this up. And then I promise I will do an implicit differentiation here before we get done. Here's the question. It's coming up in 5, 4, 3, 2, 1. If Zoom can work, there it is. That's the question. Given f of x is 2, cosecant of x, write the equation of the line tangent to y equals f of x when x is 2 pi over 3. Let's do it. What I have to do to get the tangent line is I do need to take the derivative, f prime of x. Well, you need to know the derivative of cosecant of x. Now, what's the derivative of cosecant of x? Well, it's going to be negative 2 cosecant x cotangent x. I hope I got that right. Cosecant, derivative secant. Oh, wait a minute. Yeah, derivative secant is secant tangent. Therefore, the derivative of cosecant is negative cosecant cotangent. So that's the derivative. What I'm going to do is evaluate that. If that's not right, somebody better check and make sure, because I'm going to proceed assuming that that's the right derivative. And then I'm going to evaluate that to get the slope of our tangent line. Now look, I don't want to deal with that cosecant. I'm going to do 1 over sine of 2 pi over 3. And for cotangent, that's 1 over tangent. Wow, this is really a tough one here. So now what we have to do is we have to get sine of 2 pi over. All right, students, this is Mr. Rich from the following morning after our Q&A last night where my Zoom crashed after my internet went out. But anyways, I wanted to finish this problem that a student had posted. Actually, I actually was able to come back into Zoom and finish the problem up, and she hung around and waited for me to get back on. So, but I did want to share it with the rest of you in this recording. The question was, given that f of x is 2 cosecant of x, get the equation of the line tangent to f of x when x is 2 pi over 3. And I think we got as far as maybe coming up with the derivative during the live session. But the derivative of 2 cosecant x is negative 2 cosecant x times cotangent x. That's one of the rules of derivatives that you need to know. The derivative of cosecant is negative cosecant cotangent. And therefore, what I did is I changed the cosecant to 1 over sine, and then I changed the cotangent to 1 over tangent. I plugged in the x value at which we wanted to evaluate the derivative, 2 pi over 3. And I think this is where maybe things went dark last night. But sine of 2 pi over 3 is root 3 over 2. Tangent of 2 pi over 3 is negative square root of 3. Then flipping that gives us 2 over root 3. So it's negative 2 times 2 over root 3. And then when you multiply all three of those together, you get this answer of 4/3. That was the slope of the tangent line at x equals 2 pi over 3. Then I needed to get the y-coordinate of the point of tangency, so we had to go back to the f of x function and evaluate 2 cosecant of x also at 2 pi over 3, and that was 4 over root 3. Because sine of 2 pi over 3, and again, what I'm doing here is just rewriting this as 2 over sine of x, right? The reciprocal of cosecant is sine. And sine of 2 pi over 3 already determined was root 3 over 2. So when you multiply by the reciprocal, that is 4 pi over 3. That gives us all three things that we need to write the equation of our tangent line. We know the slope, which was the derivative evaluated at 2 pi over 3. We have our x1, which is the x-coordinate of the point of tangency, and there's our y1. So plugging those into point slope, this becomes the equation of the tangent line. Okay, hope that helps. And sorry we had the technical glitch last week, but I will see you next Sunday, same time, 8 p.m. Bye.